Weather is one of the most complex systems on our planet, defined by constant shifts and unpredictable non-linearities that make traditional forecasting a massive challenge. To tackle this, I've developed an autonomous meteorological forecasting platform built entirely within the MATLAB and Simulink environments. This study utilizes a Mamdani-type Fuzzy Inference System, or FIS, which is a method that allows a computer to mimic human-like decision-making by using degrees of truth rather than simple true or false logic. This approach is particularly effective for weather forecasting because it can manage the imprecise data and non-linearities inherent in meteorological systems. The architecture is built around a multi-sensor fusion approach, integrating 4 specific inputs: the light sensor for solar irradiance, the wind sensor for anemometric speed, the humidity sensor for hygrometric levels, and the temperature sensor for ambient temperature. These inputs are processed by the Fuzzy Logic Toolbox to drive 4 localized probability outputs: sunny prob, windy prob, cloudy prob, and rainy prob. To bridge these inputs and outputs, we implement a set of heuristic if-then rules within the Mamdani system. These rules allow the model to translate raw environmental data into localized atmospheric predictions with high precision. For instance, the system follows logic such as, if the light sensor is bright and the temperature is hot, then the sunny probability is high. Other rules define that if the wind sensor detects a gale, the windy probability is high, or if the humidity is high, the cloudy probability increases. By using triangular membership functions, the system can handle fuzzy transitions, like a day that is transitioning from breezy to a gale, by assigning membership values to categories like calm, breezy, or gale, rather than using hard numerical cutoffs. The architecture even features a real-time dashboard interface that allows for dynamic manipulation of these variables, providing immediate visual feedback through synchronized gauges. Let's run our first test case in the Simulink environment. Imagine a peak summer day where the light sensor is high, the wind is low, the humidity is low, and the temperature is hot. When we run the simulation with these parameters, the fuzzy logic rules process the bright, calm, dry, and hot inputs to generate a high probability for a sunny output, while keeping the windy, cloudy, and rainy probabilities at a minimum. This demonstrates how the system effectively manages the uncertainty of a clear, hot day to give a localized prediction with high confidence. Now, let's flip the scenario for our second test to see how the model reacts to more turbulent conditions. In this case, we set the light sensor to low, the wind speed to high, and the temperature to cold. As we trigger the simulation, the FIS interprets these as dark, gale, humid, and cold inputs. The synchronized gauges immediately shift, showing a sharp spike in the probability for rainy and windy conditions, while the sunny probability drops to nearly 0. This confirmed mapping successfully translates complex environmental states into interpretable likelihood scores. Thank you for joining me for this deep dive into fuzzy logic meteorological modeling. By leveraging the power of MATLAB and Simulink, we've created a scalable framework that turns raw sensor data into actionable insights. This project highlights how digital simulations can master the non-linearities of our natural world with high precision and efficiency. If you found this technical walkthrough helpful, don't forget to like and subscribe for more engineering and simulation content.